Boolean algebra. Boolean algebra is a fundamental concept in digital electronics. It provides a formal framework for analyzing and designing digital circuits. Here are some key points about Boolean algebra in the context of digital electronics. Basic concepts. Binary variables. Variables in Boolean algebra can have two values, 0, false, and 1, true. Logical operations. The primary operations are and, or, and not, and, the result is true if both operands are true, or, the result is true if at least one operand is true, not, the result is the inverse of the operand. Boolean expressions. Boolean expressions are formed using binary variables and logical operations. These expressions can be simplified using Boolean algebra rules, which is crucial for designing efficient digital circuits. Boolean algebra laws and rules. Simplification techniques. Karnaugh maps. K-maps, a visual method for simplifying Boolean expressions by grouping ones in a truth table. Quine-McCluskey method, a tabular method for minimizing Boolean functions. Karnaugh maps, K-maps. A Karnaugh map, K-map, is a graphical tool used to simplify Boolean expressions. It organizes truth values into a grid, making it easier to visualize and group terms to minimize expressions. Create the K-map, plot the truth table values into the K-map grid, group the ones, group adjacent ones into the largest possible power of two rectangles, 1, 2, 4, 8, etc. Write the simplified expression. For each group, write down the product term, noting the variables that remain constant. Quine-McCluskey method. The Quine-McCluskey method is a systematic tabular approach to minimize Boolean functions. List minterms, write down all the minterms of the function, group minterms by the number of ones, group minterms based on the number of ones in their binary representation, combine minterms in adjacent groups to eliminate variables, repeat until no more combinations are possible. Example. Consider a Boolean expression, f equals ab f equals a.b f equals ab. This can be simplified using the distributive law, f equals a, bb, f equals a.bb, f equals a, bb, since bb equals 1 bb equals 1 bb equals 1, complement law, the expression simplifies to f equals a1 equals af equals a.1 equals af equals a1 equals a. His simplified expression indicates that the original circuit can be implemented with fewer gates, thus optimizing the design. Would you like to dive deeper into any specific aspect of Boolean algebra or its applications in digital electronics? Applications in digital electronics. Logic gates, basic building blocks of digital circuits that implement Boolean functions. Examples include AND, OR, NOT, NAND, NOR, XOR, and XNOR gates, combinational circuits, circuits whose output depends only on the current inputs. Examples include adders, multiplexers, and decoders, sequential circuits, circuits whose output depends on both current inputs and previous states. Examples include flip-flops, counters, and registers. Combinational circuits. Combinational circuits are digital circuits where the output depends solely on the current inputs, adders, circuits that perform addition. Example, half adder, full adder, multiplexers, MUX selects one input out of many and forwards it to the output, decoders, converts binary data to a specific output line. Sequential circuits. Sequential circuits are digital circuits where the output depends on the current inputs and the previous state, memory, flip-flops, basic memory elements that store one bit of data. Types include SR, D, JK, and T flip-flops, counters, sequential circuits that go through a predetermined sequence of states, registers, groups of flip-flops used to store multiple bits of data.